So, in the last lecture we finished the suffix trie data structure. Now, I want to come back to the suffix trees, because suffix tries serves as a good prerequisite to understand suffix trees, and when we are discussing suffix trees we are going to get rid of the bad properties that we saw in the suffix trie. That was, it was using quadratic runtime to build and it was using quadratic space as well. So, we are going to get rid of that in the suffix tree data structure. On the right side you see the suffix trie. So, this is the trie example for this text shown on the top. First we will try to minimize the space required to save the index, right. So, how much space does the trie need? So, the trie needs order n square space, where n is the size of your text. So, in order to reduce the space requirements, the first idea that we are going to do is we are going to collapse the non branching paths into a single edge. For example, you see that there is a long non branching path here. What I am going to do is I am going to coalesce this long non branching path into a single edge, and instead of having character labels on each edge I am going to put string labels now. So, for example, in this particular case the complete path spells $ABA. I am going to save this string label $ABA on the shortened edge, right. So, for all non branching paths in the suffix trie I am going to coalesce them. Similarly, you can see that this particular non branching path is now shortened into a single edge that spells the string ABA $. Okay, so that is the idea number 1. This is not enough right now, because we still have to store these edge labels, right. So, these edge labels are still going to occupy space if you want to represent the edge string edge labels, right. So, as a next step what we are going to do is we are going to get rid of these edge labels. Observe that when I am storing the edge labels, instead of storing the edge label I can store a pointer in the original text. So, for example, this $ABA string I can say that this is the same string that occurs starting from position 3 of the text that has length 4. So, I can equivalently store this in terms of two numbers 3, 4, that is its starting position, that is starting offset, and the length of this string. Alternatively, you can store starting and ending offset also, that is also okay, but in this case example I just chose to store starting offset of the edge label and the length of the edge label. So, this instead of storing this entire string I am going to store instead only two numbers 3 and 4, right. And now if I want to go back from this 3, 4 I want to recover the original string, I will make sure that I am storing the text alongside my tree, so that I can use this pointer 3, I can go back to the text and recover the original string back. So, when I am doing pattern matching I may need those edge labels, right. So, at that point I am going to use the text and access those strings whenever I need. So, it turns out okay. So, these two ideas, and the last minor point I want to add is that I am also going to store the suffix IDs on the leaf nodes, and that is just for convenience. So, for example, this particular leaf node represents the suffix starting from position 0. Similarly, this is this particular leaf node, if I spell the path from root to this leaf node, then this spells the suffix starting from position 2, that is $AABA. So, this may also is convenient, because when I am solving many problems and I reach the leaf node I can immediately tell that this is the leaf node corresponding to suffix that starts at position 2, right. So, this will be helpful while problem solving. Okay. So, now given these two properties, have we addressed the space limitation of suffix tries, that is, are these two property ideas sufficient to reduce the space requirement from quadratic to subquadratic, or let us say linear time? Well, it turns out yes, and we will see why. So, in the next slide onwards, I am not going to show you the edge labels in terms of offset and length. I am going to use the string labels themselves, because that allows for easy visualization. However, when I am implementing in a software, I am going to use the offset and the length, but for here, for the visualization purposes, I am going to show you the actual strings. Okay, so let us look at the properties of suffix tree. The first property which is important is that every internal node has at least 2 children. Why? Well, that is because where we have collapsed the non-branching paths. So, it can never happen that a suffix tree, in a suffix tree you have an internal node which has only one children, because if you see, if it has only one children, I would have collapsed this 2 edges into one edge only. So, therefore, when we have collapsed these non-branching paths, we make sure that each internal node has at least 2 children in the suffix tree. You can also see in the right hand side example that every internal node has at least 2 children. The next property is that the count of leaves is n, which is same as the suffix tree, because we have n suffixes, and for each leaf node represents a suffix id. So, if you go from a root to any leaf node, that is going to spell a suffix. So, therefore, the count of leaves is exactly n. Now, these two properties combined, what we get is the number of internal nodes cannot exceed n minus 1. Why? Well, intuitively you can think that if I cannot have any situation where the tree has many internal nodes and too few leaves, right. So, this normally happens that when you have too many internal nodes and too few leaves, that will happen only in this scenario where you have a non-branching path, but these situations cannot occur in a suffix tree. So, if the suffix tree has many internal nodes, then it will have many leaves also, right. So, these two will grow proportionally as the suffix tree data size is increasing. We can prove this inequality formally as well. So, let us do that, right. So, let us prove that the number of internal nodes in the suffix tree cannot exceed n minus 1. For proving that statement, we have to recall some basic properties of a tree. So, remember that in a tree, the number of vertices is exactly equal to the number of edges plus 1, and that you can easily prove by induction, right. So, this you can easily prove by induction. In fact, you can try this on your own, easily provable using mathematical induction. And the second property that we are going to be needing is that if you sum up the degree of all the vertices, then that is equal to 2 times the number of edges, and that is also trivial, because when we are adding the degrees of all nodes, we are counting the edges twice. So, therefore, this equality also is trivial to understand. So, with these two basic properties, we can prove the inequality for suffix trees. So, we are given a suffix tree st, and in suffix tree each internal node has one parent node and at least 2 children. Suppose capital I denotes the set of internal nodes in st and capital L denotes the set of leaf nodes in suffix tree. The claim is that the number of internal nodes is less than equal to number of leaf nodes minus 1. So, let us see the proof, and it is a short proof actually. So, basically we can start with this basic property that 2 times number of edges is the sum of degree of all vertices, right. And we also know that the number of edges is equal to the number of vertices minus 1. So, that we can replace that the number of edges with number of vertices minus 1, right. So, this so far the equation is simple. Now, we have to observe that the set V, that is a set of vertices or set of nodes, includes a root node, leaf nodes L and internal nodes capital I. So, I can split my equation into these three categories of the nodes. So, root node, leaf nodes and internal nodes. So, when I do the split, the left hand side equation becomes L plus I plus 1, right, and the minus 1 here. So, this minus 1 will cancel out. On the right hand side, I am summing the degrees of all the vertices. So, now I can sum the degree of root node, I can sum the degree of all the internal nodes, I can sum the degree of all leaf nodes. Okay. So, now what is the degree of a leaf node? Well, the degree of a leaf node is exactly 1, because the leaf node has no children and it has one parent. So, the degree of leaf node is exactly 1, right. So, this summation we can easily resolve to L. What about degree of root node? Well, degree of root node must be at least 1, because it has at least one children, and for internal nodes they have one parent node and they have at least two children. So, for each internal node my degree is going to be at least 3, right. So, to state that formally, so degree of root node is at least 1, degree of a leaf node is equal to 1 and degree of an internal node is at least 3. If I plug these inequalities in my equation, what I get is the left hand side 2 times L plus I is greater than equal to 1 plus 3 times I plus L. And if I just simply resolve this inequality, what you get is what we wanted to prove, that is the number of internal nodes cannot exceed the number of leaf nodes minus 1, right. So, this was a straightforward proof to prove that the number of internal nodes in the suffix tree cannot exceed n minus 1. Now, why is this important? Because you can easily see that in the suffix tree there is a single root, we have n leaves and we have at most n minus 1 internal nodes. So, therefore, the total number of nodes in the suffix tree is linear in terms of the text size, right. So, this is very crucial property to argue that the space requirements of the suffix trees are going to be linear, because observe that each edge uses order 1 space, because we are for each edge we are storing 2 numbers, that is the offset and the location, sorry, the offset and the length of the string. So, this is constant, right. So, instead of string labels we are storing these offset length tuples, therefore, each edge uses order 1 space. Similarly, each node also uses order 1 space, because each node will have to keep pointers to its children, and any node can have at most sigma pointers, because we cannot have no two edges can share same initial characters, right. So, we can never have a situation where there is a vertex and there is a edge ABA and there is a edge ABA, because these are both starting with the same characters and that is not possible. So, the number of children of each node is less than equal to sigma, and if we assume that the size of alphabet is constant again, then we can again say that each node uses order 1 space. If you combine all these properties, what you get is that the space requirements of suffix tree is linear, that is order n, right. So, we have improved from suffix trees which were requiring order n square space. suffix trees only use linear space in terms of the text size, and all the queries that we were able to answer using suffix trees, we can also answer them using suffix trees in the same way. So for example, if I want to check whether pattern P occurs in text T, all I need to do is again start from the root node, start matching the pattern characters and see if I can match all the characters of the pattern until the last character of the pattern. So in order P time, I can answer whether the pattern P occurs in the text T or not. What about if I also want to report all the positions where the pattern occurs? Well, for that I will start matching my pattern from the root node, right. I will go until I have finished matching all the P characters of the pattern, right. So all the P characters have been matched, and then I am going to stop at this node and I look at the subtree below this node. All the leaf nodes in this subtree will tell me the suffix IDs at which the pattern is matching. So a linear traversal of this subtree will give me all the occurrences, right. Now observe that the number of this, what is the size of this subtree, because if I want to traverse this subtree, I will have to do a linear time traversal like a breadth first search or a depth first search. But we can argue the same property here, that the number of internal nodes is going to be less than the number of leaf nodes in this subtree. So therefore the time I spend to do this traversal is OCC, which is, if OCC is the number of leaves in this subtree, then I can finish the traversal of this entire subtree in order OCC time as well, because the size of the subtree is going to be linear in terms of the leaf nodes, right. So therefore if I want to report the occurrences as well, this is solvable in order P plus OCC time, where the OCC time comes from the linear time traversal of the subtree at the node where the search ends, right. So that is why we started with saying that the suffix tree can solve this pattern matching problem in optimal time, because we have to spend at least this much time reading the input and reporting the output to the user. So the input output complexity is already P plus OCC, and if the algorithm is using P plus OCC time, that is the best we can do. We can not beat theoretically this runtime for solving this problem. So far suffix tree has given us the best runtime for solving this problem compared to other data structures such as Z array or suffix trie. Okay. What about construction of suffix trees? Well, we can still follow the naive way of building suffix trees, where that we can add one suffix at a time. So for example, if I may suppose I assume that I am adding T0, suffix T1, suffix T2 and so on, I can, for next suffix Ti, I can search my suffix Ti in the intermediate tree, and until the point I can search it, at that very point I can add new edges as necessary. So for example, in the right hand side example, if I have already added the first two suffixes T0 and T1, and now I am going to add the suffix AA $. Well, observe that I will start searching for this AA $. Pattern. So in this case I am able to match the first character, but I have a mismatch from next character onwards. So all I have to do is to split this edge. So for example, I will split this edge from A onwards, and the original edge will go on the left, and I will add a new edge AB $, here to spell my new suffix AA $. So I can incrementally add new suffixes in this tree, and for example I can handle both cases. For example, my search of a pattern may end in the middle of an edge, or my search may end at internal node. In the first case I may need to break the edge into two. For example, here I have to break the edge into two. In the second case, if a search ends at an internal node, then I just need to add a new edge for the unmatched part, right. So again this algorithm is very similar to what we use to build suffix tries, and unfortunately again we are spending order n squares time, because for every suffix we are starting it by searching it in the intermediate tree. That means that we have to look at every character of the suffix. Therefore, we are spending order n square time, because that is the summation of the length of all the suffixes. Now, can we do better? Well, the answer is yes, and that we will see in the next lecture onwards. Let us also look at the relationship between suffix trees and suffix arrays. If I sort all the leaves of the suffix trees in lexicographical order, then you can easily see that I get the suffix array back. So, for example, if I order the leaf node dollar followed by I dollar and so on, then that basically means that I am sorting all the suffixes in linear order, in lexicographical order, and then I get back my suffix array. So, for example, you can do a depth first search of the suffix tree and produce leaves in the lexicographical order. We have to be careful in the sense that when we do depth first search, we have to prefer the lexicographically smaller edge first. So, the dollar edge should be visited first before PPI dollar, before SSI dollar. If we do the depth first search in that order, then we will, the order in which we visit the leaf nodes will be equivalent to the suffix array, right. What about going back from suffix array to suffix tree? Is it possible? So, can we, suppose I built a suffix array using prefix doubling algorithm and I give you the suffix array. From suffix array, can you build suffix tree? So, that will be the key intuition that we will be using in the next lecture, that is, we will come up with a faster algorithm to build suffix trees. So, instead of order n square algorithm here, which is very slow, we will be using this strategy of first building suffix array using prefix doubling, which takes n log n time only, and then we are going to process suffix array and get the suffix tree out of it. So, that we will discuss in the next lecture. So far, I will summarize what we have discussed. So, suffix trie offers a natural way to index suffixes of a string. It can answer many queries such as searching, counting occurrences very trivially. However, it occupies too much space and it required too much time to construct. We saw that suffix trees use linear space only. So, therefore, we could get rid of the space issue that we had with suffix trie. We have to get rid of time issue as well, and that we will do in the next lecture. We will show that it is possible to build suffix tree in time better than n square. And finally, I want to emphasize that suffix trees can be used to solve many non-trivial string problems, not just the exact pattern matching problem, but many other problems, and some of the examples we will see in this course as well. So, with that we will close and we will repeat the suffix tree data structure construction in the next lecture.